It's time for the second lecture in the atmosphere module, and the focus today is on atmospheric radiation and the greenhouse effect. So radiation, by definition, is energy transmitted by electromagnetic waves. All objects, whether inanimate, animate, you name it, absolutely everything emits radiation. And that's just from essentially the fact that there's molecular motion happening in all objects. However, an object can emit radiation at a particular wavelength only if it absorbs radiation at that same wavelength. So here you can see the electromagnetic spectrum, which I'm assuming most of you are already familiar with. To the right is increasing wavelength, and to the left is increasing energy. So the shorter the wavelength, the more energetic. So your gamma rays and X-rays on the left, things that are very harmful to you, and you hit the ultraviolet. And then the narrow strip of the visible wavelengths from 400 to 750 nanometers, which have a big impact on Earth, obviously. And then the infrared. We don't worry too much about microwave and radio waves when it comes to talking about, Earth's radiation balance. The first concept that I want to introduce when thinking about radiation and the greenhouse effect is the concept of a black body. And the sun, it turns out, emits electromagnetic radiation over the entire electromagnetic spectrum. However, it's most concentrated near the visible. And if you look at the wavelength here, you can see that that's the sort of peak, 500 to 1,000 nanometers here, about the peak of the visible. So a black body is something that is an object, or known as a body in this case, that radiates the maximum possible intensity of radiation at every wavelength for a given temperature. And so what you see on the figure here in blue is the sort of idealized expected curve for a black body that has a temperature of 5,782 Kelvin. In red is the actual emission spectra for the sun. And you can see that that blue line is a pretty good fit to the actual observations for the sun. And so that's what we mean when we say that the sun acts as a very efficient black body. And all of this is temperature dependent. So at a given temperature, there's a maximum amount of energy that can be emitted per unit time per area of a body. And that's what the blue line here is showing. And so most things don't act as a black body like this, whereas the sun does. It makes it a little bit easier to sort of handle in calculations and things like that it acts so idealized. So what does it mean to be a black body emitter? Black bodies emit radiation at all wavelengths, although from the previous graph you can see not necessarily the same amount at all wavelengths. The emissions peak at a wavelength that is inversely proportional to temperature. So the higher the temperature, the lower the wavelength that they peak at. And the total radiation flux emitted by a black body, so if you want to sum all of that radiation up, simplifies to this fairly straightforward equation, where sigma is a constant, known as the Stefan-Boltzmann constant, and T is the temperature of that object in Kelvin. And so it's a constant times the temperature raised to the fourth, and it gives you your total radiation flux. So all we need to know is the temperature of the sun, and we can very quickly determine the total radiation flux. This is true for any other object as well, anything that's a black body at least. So the solar emission spectrum, so again, that's what we're looking at here, the wavelength on the x-axis, now in micrometer instead of nanometer, where the UV and visible and IR areas are identified with this line on the bottom. And this is a view of the solar radiation spectra measured from a satellite outside Earth's atmosphere. And so that's this sort of dark, thicker, solid line. It's essentially the same as the red line from the previous figure. And the dashed line is the idealized black body line. And you can see that those match up quite nicely. So solar radiation peaks in the visible. The absolute maximum happens in the green. But what's interesting about this is the thinner black line, so that's this line here, is this same measurement of the solar emission spectra, but now it's sea level. So when you take it at sea level, it means that you're looking at the sun's emission spectra from Earth's surface perspective, meaning that now this solar emission spectra has been influenced by the atmosphere. And what's interesting about this is that you can see a couple of things. First, there's some reflection by clouds that happens, and so this maximum has been brought down quite a bit. But the other thing you see now is it's quite jagged. You see these jagged lines here. And so that's quite different. And these are called absorption bands. So something in the atmosphere is absorbing this electromagnetic radiation at these particular wavelengths. And it turns out that these are the gases in the atmosphere. Okay, so, and we'll talk more about that, right? That becomes very important, that these gases are absorbing radiation. Okay, so now we can also treat the Earth in the same way. Obviously, the Earth isn't nearly as hot as the sun. So here, this is a satellite view of Earth's emission spectrum under clear sky conditions at a particular location. And you'll see now we've got wavelength up here on the top x-axis in micrometer. Now, very different numbers if you look than here. 0 to 3 is the wavelength in micrometers. Now we're much higher numbers. And that's because the Earth is much colder. So the Earth doesn't emit at the visible range at all because it's much cooler than the sun, which makes sense because then we wouldn't have dark nights if we had visible light from the Earth. And you can see the Earth is not a super great approximation of the black body. So the dashed lines here are idealized black body curves at various temperatures that are sort of close to the surface of the Earth temperature. And there's a lot more of these jagged peaks in the terrestrial emission spectrum, and that's because the Earth's emission spectrum is influenced by all of these gases that you can see, these atmospheric gases that are leading to these absorption bands. So we can calculate in a fairly simple manner the radiative balance of the Earth. We know that the Earth must be in energetic equilibrium in the sense that the radiation it receives from the sun and the radiation that it emits out to space have to be equal. And we know this because the Earth isn't heating up and getting ready to explode any second. So these things have to be balanced. And so first we can look at the total radiation emitted by the sun, which we've denoted here as E sun per unit time, which is essentially the total radiation flux, which I've already said is this constant times the temperature of the sun raised to the 4th, times the area of the sun. And so this is 4 pi, the radius of the sun squared. So you can Google fairly easily what the radius of the sun is and what the temperature of the sun is. And that gives you the total radiation emitted by the sun per unit time. So this is what's actually making it to Earth. But of course, there's one other thing to remember, which is that the Earth is at some distance from the sun. And we have to take that into account as well. So what's the solar radiation flux across that distance? So Earth is pretty far from the sun. Again, a fairly simple number to look up, about 10 to the 8th kilometers. And so the solar radiation flux across that distance, we assume, is distributed evenly over the Earth. And so we treat this essentially as a disk that has a solar radiation flux. The Earth itself has a terrestrial radiation flux, and there's a distance between these two fluxes of d. So it's a simplified model, but it works pretty well. Okay, so using this concept, we can calculate Fs, which is the solar constant for the Earth. And so this here on the right-hand side, so we've got our Stefan-Boltzmann constant times the temperature, and then the radius of the the radius of the sun divided by the distance from the Earth to the sun. And so this is what's arriving to the Earth, and then this is what's leaving the Earth. And so what we can get here by calculating Fs, the solar constant, is the solar constant for the Earth. So this is based on the radiation that's coming from the sun the size of the sun, and the distance between the sun and the Earth. So, of course, because you can calculate this for other planets, right? You just need to know the distance from that planet to the sun to know what the solar constant for other planets is. But nevertheless, so this is basically the solar constant for Earth. This is what we're getting on Earth. 1,370 watts per square meter. And then, so the other thing to remember is that the fraction of the solar radiation flux received per unit area of the Earth is actually a quarter of the solar constant. And that has to do with the fact that these things are spheres, right? I'm not going to get into the geometry or the algebra of it. But essentially, because we've got two spheres here, it's equivalent to a quarter of the solar constant if you want to look at it per unit area. And so that's actually 342 watts per square meter. Okay. So based on the temperature of the sun, the fact that it's a good black body, the area of the sun, and the distance of the sun from Earth, combined with the fact that Earth is also a sphere, has allowed us to get to this number of 342 watts per square meter as the incoming solar radiation. We can use that to try to understand Earth's annual global mean energy balance. And so everything in red here is incoming solar radiation. And so what happens to these 342 units? 168 of those units are absorbed by the surface. 77 of them are immediately reflected by clouds and aerosols in the atmosphere. So that's basically, some of it comes in and 77 units just immediately go out. And then the surface of the Earth also reflects some solar radiation. So that's these 30 units here. So of the 342, 107 are pretty much immediately reflected back out. And this process of how much is reflected back out immediately is this is known as the albedo of the Earth. Okay, so we've lost basically a third of the incoming solar radiation to reflection. Some of what the additional radiation is absorbed by the atmosphere. Okay, and then the other thing to keep in mind here is that the Earth itself is radiating out. The Earth has its own sort of radiation because it also is emitting. So this is what's emitted from the surface. It's 390 units. Okay. Some of them go right through the atmospheric window, which I'll show you in another slide coming up soon. Some of this heat is released through evapotranspiration, latent heat, but some of this long-wave radiation emitted by the Earth is captured by greenhouse gases, and that's what comes back down here. All right, and you can see it's actually quite a bit of it that's captured. Some of it, of course, ends up being emitted by the atmosphere. Okay, so that was the sort of overall picture. I'm going to go through some of this a little bit step by step. So of that incoming radiation, a fraction of it is reflected back to space by clouds, snow, ice, the surface of the Earth, and this is known as the planetary albedo. We can measure this via satellite. I showed you what the solar emission spectrum looks like outside Earth's atmosphere, and then what it looks like at sea level, and this gives you a sense of planetary albedo, and it's about 0.3. And if you look here, 107 out of 342 is about 30%, so that makes sense. So the mean solar radiation flux absorbed per unit of the Earth's atmosphere is then that Fs value divided by 4 times 1 minus alpha. So if alpha is 0.3 gets reflected back, it means that 30% gets reflected away, 70% is actually available. And so that's how you get that, that's where these numbers come from. Okay, so this absorbed energy, so you've got energy that comes in, some of it's reflected away, but 70% of it stays, okay? And that's what's being given here on the left. Some of that has to be balanced by the emission of terrestrial radiation out to space. And that you get from this sigma constant, times the temperature of the Earth raised to the fourth. So that's essentially getting at these long-range numbers of what are coming out. Okay, what's cool about this is that we know these two things must be balanced because the Earth isn't heating up. And so we know the solar constant, we know albedo, and we know sigma, which means we can calculate what the temperature of the Earth should be. And we call that the effective temperature of the Earth. So just basically did some algebraic rearranging here to solve for TE, the temperature of the surface of the Earth. Whoops. So if you do this, and this is just, a slide here, just a reminder of the unit conversions, because now we're dealing with temperature in Kelvin. It's not degrees Kelvin, it's just Kelvin. See, degrees Celsius, degrees Fahrenheit, and Kelvin. Okay, so using this constant 0.3, our calculated solar flux, we calculate that the temperature at the surface of the Earth is 255 Kelvin, which if we convert using the previous slide means the temperature of the Earth on average is minus 18.2 degrees C. So that is clearly not true, right? It is not on average minus 18 degrees C on the surface of the Earth. The average surface temperature of the Earth is much higher than this. So why is that? Well, the reason has to do with a big chunk of what's missing in this equation, but what was present in that diagram. So that's that some of this radiation is absorbed by the atmosphere. And so how does that work? Here we have the emission spectrum of the sun and the Earth. Now up here, the Earth has been idealized as a black body, even though I said it doesn't make a very good black body. And the sun is much hotter than the Earth. Okay, and so as a result, the Earth, because it's much cooler, it radiates at longer wavelengths. And here you can see, so there's a couple of things. So gas molecules in the atmosphere absorb radiation of a given wavelength if that energy can be used to increase the internal energy of the molecule. So gases that absorb in the wavelength of 5 to 10 microns, which I've denoted by this red bar here, those gases become really important because that's the wavelength where a lot of terrestrial radiation is emitted. And you can see down here, the gases that absorb really well at those wavelengths are methane, nitrous oxide, CO2, ozone. Okay? So, and what are those? What do those things have all in common? Well, they're all greenhouse gases, right? And so because of the way these molecules are put together, they're absorbing radiation that is being emitted from the Earth. And so this plays a really important role because by absorbing that radiation, they're not allowing it to leave. They're actually trapping it on the planet. And as a result of trapping that radiation, they're raising the temperature of the surface of the Earth. The other thing I wanted to point out here is this atmospheric window, which is a little bit longer in wavelength than the greenhouse gases. And this allows direct escape of radiation from the surface of the Earth to space. And this is also important in defining the temperature of the Earth's surface. So it's this little window here where radiation can leave really easily. Okay, so this 40 units goes out the atmospheric window, but it's this process, the fact that greenhouse gases can absorb some of this radiation and bring it back down is really important in terms of warming the Earth. And then some of this energy is, of course, also immediately absorbed by the atmosphere. But you can see it's not a lot. So the greenhouse effect isn't because greenhouse gases absorb solar radiation. This number is quite small. The greenhouse effect is because greenhouse gases absorb Earth's radiation. They absorb this long wavelength stuff, and then they re-radiate it back down and keep things warm. So again, look back over here. The greenhouse gases aren't directly absorbing Earth's radiation, right? That's not what's happening here. It's the terrestrial radiation and these longer wavelengths that the greenhouse gases are absorbing, and that's what's actually leading to the warming of the atmosphere. So we can look at this in a fairly simple greenhouse model where we make some simple assumptions. So if we pretend that, so this is the surface of the Earth, and this is the atmosphere. It's this little gray box here, gray rectangle. And we assume it's a fairly simple isothermal layer, so it doesn't change its temperature, and we place it above the Earth. So we know from looking at those various wavelengths that the incoming solar radiation goes down to the surface of the Earth, and it, for the most part, doesn't really interfere with that atmospheric layer much at all. It hits the surface of the Earth. Okay, we also know that the surface of the Earth has a temperature of T0, and that it has its own radiation as a black body, given by the sigma T0 the fourth here. So we've got incoming solar radiation, and then we've got outgoing terrestrial radiation. So if we assume that the atmospheric layer absorbs some of this terrestrial radiation because of the presence of greenhouse gases, we can denote that by F, just saying a fraction. So of this energy that radiates off the Earth, some fraction of it is going to be absorbed by the atmospheric layer. And so I realize we just went from somewhat simple to somewhat more complicated, but let me just sort of step you through it. And I'm not going to ask you guys to recreate this. It's just kind of a simple thought exercise. Okay, so this is what's coming in from the sun. Okay, that's fairly straightforward. We've got here what's coming off the Earth, and then it hits this atmospheric layer, and the atmospheric layer has its own temperature, T1. Okay, so the atmospheric layer then is going to radiate in both directions, because the atmospheric layer is itself, an object that emits radiation. So sigma times the atmospheric layer's temperature to the fourth is going in both directions. And of course, some fraction of that is going to be absorbed by the atmosphere. So whatever is not absorbed by the atmosphere is 1 minus F, right? It's whatever's left over. So of this terrestrial radiation, some of it's absorbed by the atmosphere, and whatever's non-absorbed goes away, okay? So what we end up with mathematically is this bit that doesn't get absorbed by the atmosphere and just goes away is here, okay? And then this bit is what's absorbed by the atmosphere. Okay, so that's this here. Well, actually easier to think of it this way. So we've got our into Earth, and then what leaves the Earth is this plus this, okay? Because this plus this will sum to this box. All right, so we can simplify that a little bit. And what we can see is that this F sigma T0 to the fourth has to be equal to this, right? So what's absorbed and then re-emitted by the atmospheric layer has to be equal. And if you substitute a little bit and do a little bit of rearranging, what you end up with is a situation where you can solve for the average surface temperature of the Earth. But really, we don't need to solve for the average surface temperature of the Earth. We've measured the average surface temperature of the Earth. We know what this is. What's interesting about this is we can use what we see as the average surface temperature of the Earth to calculate F. Because this F is essentially the greenhouse effect of the atmosphere. It's how much of this terrestrial radiation is being absorbed by the atmosphere and re-radiated back down to warm the Earth. So we had calculated that the effective temperature of the atmosphere was about minus 18 degrees C. Of course, then that's very different from the observed temperature of the atmosphere. So if we go forward, so if we know the observed temperature of the atmosphere and we calculate F, we end up with F being 0.77. So what that means is the only way to account for the observed average surface temperature of the Earth is if the atmospheric layer, essentially the greenhouse effect, absorbs 77% of terrestrial radiation. And so that's how we go from minus 18 degrees C to a more reasonable number, which I think is something like 20 degrees C or 18 degrees C positive, something like that. Okay? So I hope you guys sort of followed along that. I'm not expecting you to do this mathematically. I just wanted to show you that figuring out the impact of the greenhouse effect doesn't necessarily have to be done by some super sophisticated fancy model. if you know some basic things about the sun, and you know some basic things about the Earth's albedo, and by assuming that the sun and the Earth are both black bodies, and you know their temperatures, you can play around a little bit, do a little bit of algebra, and get at this 77% number. The other thing that's useful about this exercise is it shows you quite directly that if you increase F, meaning if you put more greenhouse gases in the atmosphere, you essentially increase F. If you increase F, if you make F a bigger number, you're going to make T0 a bigger number. And so again, this is a fairly simple way to see that the concentration of greenhouse gases in the atmosphere are really important for determining the surface temperature of the Earth. And yes, there's tons and tons of complexities, and climate models are massively complex. But for a sort of first order effect, using some fairly basic principles, you can get at this idea that the greenhouse gas layer in the atmosphere is really important for controlling the surface temperature of the Earth. Okay, so I hope that's helped shed some light on these various numbers and what happens to the incoming solar radiation, and how the greenhouse gases are really important for getting this terrestrial radiation back down. And that if you go through and you sum up all these numbers of what's coming in and what's going out, you'll see that it is actually in balance. So the last thing I want to leave you with before we go is moving on from the concept of radiation to the concept of radiative forcing, because you hear a lot about radiative forcing when we're talking about greenhouse gases. So radiative forcing, by definition, is a measure of the net change in the energy balance of the Earth system in response to some perturbation. So if we look at this is the energy balance. And so when we talk about radiative forcing, it's about how has this entire energy balance been altered by some change to the Earth's environment. And so, of course, one way, probably the simplest to think about it, is, well, if you increase F, if you increase the amount of greenhouse gases, you're going to alter this energy balance, right? First thing you're going to do is alter this number here, how much is sent back. But there's trickling effects that happen all throughout this. And it's not just greenhouse gases that influence Earth's radiative forcing. There's ozone, stratospheric water vapor. There can be changes in the albedo of Earth because of land use. And then aerosols play a really big, important role in Earth's cooling, which we're not going to talk about much now, but we'll talk about next term. And so all of these things add up to influencing Earth's radiative forcing, or I should say changing the net energy balance of the Earth system. And so this concept of radiative forcing obviously can't be calculated using the fairly simple model we developed here, because the little simple model we looked at here just had an F term for showing the absorption of greenhouse gases. So the way this is done is with the use of what are called general circulation models, or GCMs. And these actually resolve all of the horizontal and vertical heterogeneity, so the sort of unique features of Earth's surface and the atmosphere. And it does this three-dimensionally all over the place and conserves energy, mass, and momentum. And so what's cool about this is in GCMs, if you have some sort of radiative perturbation, or let's say an increase in a greenhouse gas, so it triggers that initial warming, which we saw from our very simple equation. But it also then allows for really complex responses. So enhanced evaporation of water vapor from the ocean, changes in cloud cover, changes in atmospheric and oceanic circulation, and so on and so on. And so the other thing about radiative forcing is what we can do for things that are non-greenhouse gas related. You can relate other gases to a reference gas so that we can sort of quickly look at what we call the global warming potential for various gases. And so I just wanted to introduce this idea because this is something that you guys might be seeing in some of your other courses. And so global warming potential is the time-integrated global mean radiative forcing of a pulse emission of 1 kilogram of some compound relative to that of 1 kilogram of CO2. Okay, so that's a really weird definition, but what it basically means is if CO2 gives you 1 unit of global warming, okay, how does everything else compare? So methane gives you 21 units of global warming. as compared to CO2, which means methane is a much stronger greenhouse gas than CO2. N2O, nitrous oxide, gives you 300 times the global warming power of CO2. And so it's a way, and the reason you think, wow, how come we don't worry more about nitrous oxide and methane? Well, we do, but the reality is that the human changes to methane and nitrous oxide haven't been as big as the human changes to CO2 emissions. And so it's a way to sort of simply evaluate trade-offs between emissions of different gases. So if you were to say, I have to make this choice in a policy, and it will reduce CO2 emissions, 10 units of CO2 emissions, or 100 units of N2O emissions. You could look at this and say, well, actually, the 100 units of N2O emissions are definitely going to give you much better bang for your buck. You should reduce those than reducing your 10 units of CO2 emissions. But the reality is, if you were to reduce 1 unit of nitrous oxide versus reducing 10 units of CO2, it's still better to reduce the nitrous oxide because it's so much stronger in its global warming potential.